at exponential growth and decay. And I know in this class, a lot of the math that we do, um, it doesn't always feel that it has a connection outside of the classroom, right? I understand that. And a lot of school math kind of feels that way until you get into some of these more advanced classes. And you all are really close to that. Like when you get to pre-calculus and calculus, the applications that you can start applying that math to grow by quite a bit. The reason I bring that up now is exponential growth and decay is, to me, the most relevant maybe topic that you are learning in this class that applies to you all outside of the classroom. And maybe not yet, but these things are coming. Okay, so exponential growth and decay. Applications that you're going to see with this are like investment accounts, saving accounts, even like credit cards. Okay, credit cards kind of follow an exponential growth or decay when you aren't paying off the bills. Okay, when you take out a loan to buy a home. Okay, these are going to be modeled by exponential equations. So this feels a lot more relevant outside of the classroom, at least to me. And you'll see that with some of the examples that we're going to go through. Yes, some of them are still kind of like classic classroom problems, but a lot of them are going to be very real to you all very soon. Okay, if maybe some of you are already dealing with some kind of exponential growth or decay outside of the classroom already. So let's start with what the equations look like. Exponential growth is going to be y equals a, and then 1 plus r to the power of x, and then the decay is a 1 minus r to the power of x. A in both cases is your starting amount. R is your percent growth, or it could also be given as a rate. Okay, if it's decay, it's going to be percent decay or a rate of decay. And then X is your time. There that we haven't defined is that one. I'm going to come back to that one in a second after we've gone through an example and built this equation. But like some of our other applications, the main thing that we need to work on is building that equation. Once we have our equation built, it's just calculator work from there. We're just going to plug everything in. But with these problems, we need to find that keyword that tells us whether or not it's exponential growth or decay. We need to identify that starting amount, and then how much we're either, whatever our rate is, whether we're growing or decaying. So we'll do like one example, and I'll have you all do the second one, and then the next two will kind of be examples for you to work on as part of your assignment. So it says the initial population of Nerdville is 12,456. The population is declining. There's that key word telling us which equation we're going to use. Okay, so this is exponential decay. So we're going to subtract our percent from 1, and I'm going to talk about why that 1 is there here in just a second. And it's at a rate of 3.85%, and this happens each year. Okay, so kind of keeping track of the time is also important with these, especially if we're given different units of time. We might have to do some unit conversions with that. It says write an equation that models the population decline of Nerdville and use your model to predict the town's population in 10 years. Okay, so that time is matched up with what the equation is going to represent, so we don't need to do any sort of conversions here. And so our equation is y equals the initial amount of 12,456, and then 1, and it's minus, when we take this percent, 3.85, we need to convert that to a decimal, right? 3.85%, I'm not taking 1 minus 3.85. Remember that percentages, it's really that percent out of 100. Okay, so to convert to a decimal, if we take the percent and divide it by 100, that equals our decimal version. Now, you can always divide it by 100 in your calculator, there's a shortcut to all of this, and that's that if you take the percent and you just move the decimal 2 to the left when you're dividing by 100, you get that exact decimal correlation, okay, or whatever the decimal form is. So 3.85% is really 0.0385. So that's the one thing we always need to remember. Don't just plug the percent in. You have to think about what is that percent representing as a decimal. So 1 minus 0.0385 to the power of x. Okay, and that's our equation. I should have put that in the box there. Now, one thing I'm going to encourage us to do before we actually plug everything into the calculator is this 1 minus our percent. Let's figure out what that is. It just makes the actual calculation part a lot easier, and we're going to limit our kind of opportunities to make mistakes within the calculator. So 1 minus 0.0385 is 0.9615. So really our equation is y equals 12,456 to the power of x. All right, so before we find how much the population is going to be after 10 years, I want to come back to why this 1 is here. Okay, that 1 in all our equations is there to represent the 100% of what we started, right? If we're taking a population and we're losing 3.85%, this base in our exponential equation is basically representing how much of the population is sticking around. Well, if we're losing 3.85%, we're really hanging on, or there's going to be 96.15% that is sticking in this town. Okay, so that 1 is there to represent the initial 100% of whatever it is that we're working with. So when it's growth, we're taking the 100% and we're adding our rate onto that. So we're keeping the initial population and adding our percent to whatever that amount might be. When it's decay, we take the 100%, we subtract that rate, and thus we get some base that's between 0 and 1. So again, think about this base as being how much are we keeping as we move forward. Okay, if it's decay, that value should be less than 1. If it's growth, it should be greater than 1. And in fact, I want to add that into our notes here. So exponential growth, the base, and when I say base, that's the 1 plus r. Every exponential expression has the base and the exponent. So for growth, the base is greater than 1. Right? When I take 1 and add a percent, we're going to always end up being greater than 1. So if I give you an equation, you should be able to say, hey, that represents exponential growth because the base is greater than 1. As opposed to exponential decay, where that base is now between 0 and 1. Okay? And not negative. We're not going to have negative bases. When we have negative bases with exponentials, it's a completely different thing. Okay, so we're going to decay whenever that base is between 0 and 1. So again, if I gave you an equation, you should be able to classify it as being either growth or decay based on what that base value is. Now, before I move forward with this, I just want to show you why that's the case here. It all is coming back to how exponents work. But let's say we'll just take the rate right now, 0.9615. Well, when I start taking 0.9615, which is exponential decay, and I start raising this to powers, look what happens to that decimal. Okay, when I take it to the power of 5, I'm going from 0.9615 to now 0.821. So that's getting smaller. Okay, if I then take it to something even bigger, let's take like to the power of 15. Okay, it shrinks by even more. Okay, so that's why when we have a base between 0 and 1, it's going to represent the decay. As opposed to, let's pretend I have 1.05. When I take that to the power of 5, it's going to get bigger. Okay, not by a lot, or at least 0.76. And if I now take it, so let's say to the power of 20, okay, now we're at 2.65. Okay. Okay. The last thing that we need to do is just find the population after 10 years. So now we're going to plug 10 into our equation. So y equals 12456, and then 0.9615 to the power of 10. And by us doing that 1 minus the percent, we can literally plug in exactly as we see it. We don't need to do anything odd with our parentheses. We definitely need parentheses around that base, so the calculator knows what to apply the exponent to, and to the power of 10. And I get 8,411. And with these applications, I'm not going to be super picky about rounding. Usually you want to round to what makes the most sense, right? And it's all within context of the problem. So if we're talking about population, it doesn't really make a lot of sense to say, yeah, there's going to be 0.46 of a person. Okay, so we're going to either, when we're dealing with populations or people, or even anything that like decimals or fractions of things don't make sense, we'll round to the nearest whole number. Okay, this rounding is telling us to round down, so it stays as 8,411. Okay, and that would be the population in 10 years. And I'm going to always encourage you to just ask yourself, does that value make sense? Right? Did I go from an amount and decide that this is decay and get to a smaller amount? Yes. Okay, and here we're declining by, what is that, almost 4,000 people? Okay, or just a little bit more than 4,000 people, which is quite a bit. Okay, but after 10 years, you're like, yeah, that might make sense at a rate of 3.85. Okay, so after you get that value, just doesn't make sense in terms of either growing or decaying. And if you're getting a value that's way off from where you started, that might mean that something went wrong within your calculations. Okay, why don't you all do number 2 real quick? See if you can build that equation and find the amount after 3 years. And then we're going to talk about a different type of exponential growth and decay shortly after. All right. Let's see how we did here. So once again, this problem is representing exponential decay. Again, there's always going to be some word that is telling us whether we are growing or decaying. Okay, again, in this case, that it says straight up decaying, so that makes it a little bit easier to decide. There might be some words that make it a little bit more difficult to decide if it's growth or decay, like there's appreciation and depreciation. If we don't know those words, you can always ask, and I can help you with those. But something we should become familiar with as we work through this assignment. Okay, so I'm taking 1 minus the percent. Remember to convert that percent to a decimal, so 1 minus 0.0623. That makes that base 0.9377. So again, if this equation showed up and all that you were asked is, does this equation represent growth or decay? You would say it's decay because that base is between 0 and 1. Then I'm taking it to the power of 3, and you should end with 98.94 grams. Okay, in this case, right, when you're weighing something, like a particular element, having decimal portions, right, or decimal parts that actually make sense. Again, it should specify where to round to, but I also want us to think about just what makes sense in terms of where we should round. Okay, and when it's an actual element or something that's being weighed, using decimals actually makes sense there. All right, well, any questions about either problem we just worked through here? Okay, I'm going to let you all come back and do 3 and 4 on your own. I will make an answer key for this as well, but I want to jump into some other forms of exponential growth. Okay, and that's the compound interest formula and the compounded continuously formula. So let's talk about the equation first, and I'll kind of explain what compound interest is. We still have y equals a, and then we have 1 plus r divided by n, and then n times x, or n times t. So just like before, a is your starting amount. Yeah. That 1 still represents the 100%. R still represents our rate. And make sure it's as a decimal. and then n, and n is going to be the same in both cases. That's the number of compounding periods. Okay, so that n is the exact same in both what we're going to divide the rate by and what we multiply the time by. These problems, we're given a rate that is an annual rate and it gets compounded in different ways. So x is going to represent the number of years, okay, in terms of our time. Okay, so what's happening with the compound interest formula, it's really the same as what we just looked at, but when we take a rate or an interest amount and we compound it into smaller chunks, we're basically saying, hey, let's be given a rate. So let's say we open up a savings account and we're given 10% annual interest on that. But that 10% annual interest is compounded monthly. Well, that 10% is getting divided into 12 smaller percentages that is being applied every single month. Okay, so the difference here is that the rate we're given is broken into smaller chunks, and then this is all getting applied more frequently, right? As before, when you look at the other equation, the percentage is happening over the given time. Okay, it's not broken into smaller chunks here. Okay, with compound interest, we're taking that percent, breaking it into chunks, and it's getting applied more frequently. For anything that involves money, especially if it's some sort of savings account or investment account, we want it to be compounded more often. And you're going to see that in some of these examples, that the more often we compound our interest and the more opportunities we have to add money into the account, the more it's going to grow. Okay, so compounding periods, we got to take the percent divided by the number of periods, and we have to take the number of years and multiply it by how often that's getting applied. Let's go through an example real quick, and then we'll talk about the continuously. And you'll kind of see what I mean here. So it says, determine how much an investment of $5,000 compounded quarterly. So how we know that we're using this formula, again, there's going to be words or language telling us to use it. Okay, that compounded is saying use the compound interest equation. Quarterly means that happens 4 times a year. So there's also going to be some language with these describing how often this gets compounded. So quarterly means 4 times per year. Okay, a lot of businesses operate on quarters. They have like statements or things that are due each quarter. So this is a fairly common word. And then at a 14% interest, which is pretty good. And how much are we going to get in 3 years? Okay, so for our equation, we'll build it the exact same. Just throw it there. Thanks, Sander. Starting with a starting amount of 5,000. We still have that 100%, representing that we're going to hang on to our initial investment of 5,000, and now we're going to add the interest rate of 0.147. That's me converting 14.7 into a decimal. But because that percentage is getting compounded quarterly, that 14.7% is getting divided into 4 smaller chunks. And then with this getting applied, or us accumulating interest over 3 years, we're going to take this to the power of 3, but times the number of times we compound it. So that's the 4, so that same n showing up again, and then times 3. All right, so again, that compounded interest formula, it's just taking the percent, dividing it into smaller chunks, and then being applied more often, okay, rather than just every 3 years. So for this, let's do the same thing as what we did before. Let's figure out what this base is going to be, and then just simplify that, and then look to plug everything into the calculator. So I'm going to take 0.147 divided by 4, and I'm going to add 1 to that. That's pretty easy. I don't need a calculator for that. But that's my base, okay, is 1.03675, and then 4 times 3 will take that to the power of 12. Okay, so now we just don't have a ton of things that we're having to plug in to the calculator here. All right, so 5,000 and then 1.03675 to the power of 12 means that in 3 years, this account that started with 5,000, that should be X, is 7,710, and then with money, it makes the most sense to round to the nearest cent. So this is the power of investments and getting an interest rate, right? If you open this account and you throw $5,000 in there and don't do anything to it, in 3 years, you're going to have almost 50% more. Not almost, that's more than 50% than what you started with, okay? Just by doing absolutely nothing. That interest rate is pretty high. And also know that this can work negatively, right? If I open up, let's say I take out a loan to buy a car, and I take out a loan of $5,000, and I have to pay back 14.7% interest, and I'm paying it back over the course of 3 years, I'm not only paying back that $5,000, but I'm paying back an extra $2,000 or $2,700. Okay, so while this is great when we're investing, it can really hurt us financially if it's some kind of loan, okay, or something that we're borrowing money and then having to pay interest rates back. That's why credit cards can be really sketchy if you are not paying them off. You're accumulating interest, and with credit cards, interest rates are usually really high. All right, so just for the sake of comparison, what if we took the same investment from that example and compounded it monthly? See what you come up with. Okay, maybe before you even start, think about, is that going to be more, less? Is it going to be significantly more, significantly less? Have an idea? Plug that in and we'll see how we come. Okay. So you should find that you end up getting a little bit more. Okay, almost, what is that, about 40, a little bit more than 40. 0.147 is getting broken into 12 smaller chunks. Okay, and we're taking it to the power of 12 times however many years. Again, I'm going to always encourage us to figure out what this base is before we go straight to the calculator. Otherwise, you're going to need extra parentheses right there. Okay, and while this may not seem like a lot, imagine if the investment was not just 5,000 but 500,000. Okay, and how much of a difference this is going to make then. Okay, that's why like percentages and the way this gets broken to is so important, especially for any sort of like investment company that deals with like $1 million investments, right? When we start talking about like millions of dollars or tens of millions or hundreds of millions, really small percentages or differences in that percent, like we go from 14.7 to 15, it makes a huge difference, right? With an investment of 5,000, yes, it's only a $40 difference. But again, if that number is bigger, okay, this percent makes that money change drastically. Okay, and that's the power, again, of accumulating interest. All right, well, so far, any questions? We got one last thing to look at. Okay, the last equation is compounded continuously. And it is a similar idea to the compound interest formula. It's just that it's literally working nonstop. Okay, so we're not taking a percent and breaking it into smaller chunks. Instead, that interest is accumulating time and time and time again. And there's lots of applications to this. So this equation you're going to often hear referred to as PERT. So P and then E to the power of R times T. P stands for the principal, which is just a fancy way of saying your starting amount. Then the E. E is a number. Okay, that is not representing a variable. Okay, and in fact, the thing we have below here is explaining what E is. Okay, the number E, not sometimes, It is Euler's number. Euler is the mathematician that is given credit for defining this number. It is an irrational number, kind of like pi, and it's approximately 2.718. I'm not going to need you to, you don't need to memorize that, okay? You do need to recognize that E is a number, and then we're going to need to know how we can find on the calculator. I'm going to show us how to do that here in just a second. The way that we get this number, it comes from the sum of, this would be a series. You haven't gotten that far in math to know kind of what a series is, but it's just repeated values. So doing like 1 over 1 to the power of 1, then 2, changing, literally putting every integer in for x all the way to infinity. Okay, and when we take the sum of all these values, we get to that approximation of 2.718. This is one of the most important numbers in mathematics. It has applications all over the place, finance being one. And it falls in the same category as pi in that it's an irrational number, and we use, I guess you could call E a symbol. We use a symbol to represent that value. So when we see E, it is not a variable. It is a specific number. Okay, and we're going to find that on the calculator. R is still our percents, or the rate. And then T is going to be the time in years. Now, what's nice about this equation is it will always be obvious for when we need to use it, because it's going to say compounded continuously. We're going to see those words in the actual problem. If you do not see continuously, you don't need to use the per equation. All right, and we've got one example of that. And let's just write it down here, 2.718 E. Again, that's not going to be any kind of question I'd ask you. We're just going to have the calculator do that for us, because the calculator has the exact value of E already stored into it. All right, so it says determine how much an investment of $8,000 compounded continuously at a 3.3% interest rate will be after 4 years. I guess you want to grab the note page from me real quick. Yeah, you're all good. All right, so again, it's this continuously that's telling us to use this equation. And so our equation, starting with the initial amount or the principal amount, is $8,000. The base is E. And then we're going to take it to the power of 0.033. And then times the number of years, which is 4. Okay, so really the equation, this is more for when I find the amount. The equation has us using x, so that'd be 0.033x, where x is the number of years. All right, but we're trying to find how much in 4 years, so I'm going to take 8,000. And then the button E, and this is why we have calculators for lots of reasons today. But you should find every calculator, because we all have different ones, or for the most part, different calculators. Everyone should be able to find this ln button. Okay, that ln is what's called the natural log. We are going to talk about natural logs and logs when you come back from spring break. And if you look above it, okay, it's written, that value of E is right above that. Okay, so we have to press seconds and then that ln button. That'll literally bring in the letter E, or the number E, I should say number, not the letter. And then every calculator is going to display the exponent a little bit differently. With mine, it just prompts me into that exponent. Let's go ahead and put parentheses around, regardless of what you're doing there, around our exponent, because we have some multiplication that needs to happen there. So I'm going to go 0.033 and then times 4. And I get 9,128. And then 0.87 following the rounding rules. Now, I want to kind of compare what we just did with number 5, because you're like, well, if I'm investing $8,000, that's more than $5,000. And yes, we're looking at more time, so that's more opportunity to gain this interest or gain the amount into the account. So why are we not seeing quite as big as growth as we saw in number 5? Somebody answer that. Why is the growth not quite as much as what we saw in number 5? Yeah, Liam, go ahead. The interest rate is significantly lower. Okay, that 3.3, that's a lot more realistic for accounts that you might actually deal with, both in terms of taking out a loan and investments. Okay, again, it's going to be hard to find an investment of 14.7% interest. But yeah, it's all based on that interest amount. 3.3 is not, I mean, it's still significant, right? That's still gaining $1,000 or more than 1,000 by doing absolutely nothing. Okay, but the bigger the interest rate, the more growth we should see. All right, well, that's everything in terms of what I wanted to cover. You now have plenty of practice problems to go through. I'm going to work on building an answer key. Again, the whole goal of today was to be able to get you to finish this before we get out of here today. So you are all set. If you want to work on this first, that's fine. If you want to work on the exponent properties, that also works. Want both of these turned in before we go on break.